Okay, yeah, so welcome to this project and seminar SoftMC course. So SoftMC is the name of the tool that we will be using in this class to work on some DRAM experiments. But the full title of the course is, as you see on this first slide, Understanding and Improving Modern DRAM Performance, Reliability, and Security with Hands-on Experiments. So basically in this course, we expect you to work on DRAM and to analyze its different aspects, right? So some of them are performance, reliability, and security, and do this with working on real DRAM chips. And specifically, we will work depending on the projects with either DDR3 or DDR4 modules. Okay, cool. And so during this first meeting, I will cover some logistics. I will introduce you to the group. And later I will present in the second part, I will go over the presentation when we published SoftMC. And hopefully this will explain you a bit more how this tool works and what are its capabilities. And what else? Yeah, I guess this is what I wanted to say. Yeah, and in the second meeting, well, this semester we may change it a little bit, but in the second or third meeting, we will discuss the projects available that we have available for you, and later you will pick one of them to work on. Yeah, I will say more about that when I cover that part in the logistics. Okay. Yeah, I think I described some of this already. So yeah, we will learn in detail how modern DRAM, DDR4 DRAM operates. So we will be working with DDR4 DRAM at a very low level. So I think I'll get into more examples of this, but we will not access the DRAM with load and store instructions or just by accessing some arrays in a C code, but instead we will send activate, precharge, read, and refresh commands to DRAM. Yeah, more on that. We will discuss more on that later. Okay, yeah, so you will learn how to characterize DRAM using FPGA-based DRAM characterization infrastructure. Yeah, so we will deal with FPGAs in this course, but not too much thanks to this tool that will enable us to focus more on the experiment than the FPGA implementation. Yeah, and you will use SoftMC to develop your own DRAM experiments and gain hands-on experience in studying DRAM characteristics. Okay, and this PNS course is aimed at improving your knowledge in computer architecture in general, with more focus on memory systems, your technical skills in running DRAM experiments using real devices, critical thinking and analysis. So here, most of the projects have some aspect of discovering some new things, making some new observations. So here, to be able to do that, basically you need to think very critically and explore things that are not yet explored. And interaction with I didn't prepare this slide, but apparently a nice group of researchers familiarity with key research directions that we are working in our research group. And yeah, hopefully you'll also improve your technical presentation skills while presenting your project. So more on this, but basically after you're done with your project, we expect you to present what you did. And this will be your final presentation, basically what you'll be graded based on. Yeah, and overall, the key goal of this course is to study real memory devices and learn how to do that using an FPGA-based DRAM infrastructure and gain new insights on the DRAM behavior. Okay, so here you see some prerequisites. Okay, yeah, I think I cannot say this word now. Prerequisites for the course, and probably you went over these already: digital design and computer architecture. If you haven't taken this either here at ETH or anywhere else, and you don't have any familiarity with these topics, yeah, I guess you can maybe reconsider whether you really want to take this course. Okay, so it will be good if you also have some familiarity with FPGA programming, but I guess not necessary, but it depends on which projects you will choose at the end. And yeah, interest in low-level hacking and memory, interest in discovering why things do or do not work, and solving problems. Okay, cool. So this is Professor Onur Mutlu. He's a full professor at the electrical engineering department at ETH. And yeah, so here you can see the previous places he worked on. He worked at. Yeah, so here you can see his website and the best way to reach him, which is why he has the Gmail account that you see on this slide. Yeah, and like here are some of the directions, like research and teaching directions, let's say, our group is focused on, or Professor Mutlu is focused on. Yeah, and I will like say more things about this later. Okay. So a little bit more about the team. So specifically the team that will be mentoring you in this course. So yeah, my name is Hassan and this is me. I don't know like if you can see my mouse, but yeah, so this is me. And yeah, you can see pictures of some of the rest of the supervisors. I think I do not have pictures of these two. Yeah, and yeah, I guess that's it about this slide. Cancel this. Okay. And yeah, so like if you're interested on like what you're doing, or like if you're interested in general, like doing like research, either like for your, I don't know, like bachelor or master thesis, or I guess like later in your career, you want to become a researcher. Yeah, and then you can talk to us and try to know more, like learn more about what you're working on. Okay. And this is our website. And here you can see the rest of the group on this website. Okay. And here's a picture of our group. I think this is pretty recent. Yeah, and down here, this is our motto, think big, aim high. You can, again, visit the website for like, to learn more about the group. Okay, so like, let me tell you a bit more about the current research areas that our group is focused on. So like in general, we are focused on computer architecture, hardware software co-design, and bioinformatics. In more detail, we cover memory and storage. Specifically, we focus more on DRAM, flash memory, and other emerging memory technologies, and interconnects. And yeah, you can basically read like most of the rest of the list here. I won't go over them one by one. But yeah, like yeah, our group is like working on like many different topics. So there's something that I will ask you to do after this class, or like until the deadline, which is I think next Friday, next week. So there's homework 0. You can see it on the website, and I also uploaded to Moodle, where we will ask you to submit the homework 0. So this is very simple. Basically, we'll ask we ask some questions like to like describe your research interest, and like we are basically trying to know a little bit more about you. Okay, so this is important. Please submit this, because like without submitting this, you cannot choose a project to work on, and basically you won't have a chance to succeed in this course. So this is really needed, although simple. Okay, any questions so far?
Yes. Okay. Will we get access to the Moodle page soon?
Oh, you don't have access to that, right?
Not yet.
Okay, yeah, I will take care of that.
Okay, thank you.
Yeah, so for these PNS courses, it is not happening automatically. So yeah, I'll need to do that manually. Okay. So I also set up something to enable real-time, like instant messaging. So maybe like we will try to use chat.ethz.ch. I don't know if you have ever used it. Have you? Anybody?
No.
Okay. Okay, I guess it is known for other people too. So I haven't used it either, but like it seems like ETH offers such a service, and yeah, maybe like it will be good to use that instead of like some other alternatives. Yeah, we'll see. Okay, so some requirements and expectations. So attendance is required for all meetings, but we won't have too many meetings. I guess in the first week we will have like So, okay, we will have at least one more meeting. I'm not sure about the third meeting. Maybe we will see based on like how much we will cover in the second meeting. We also expect you to study the learning materials. We already shared all of learning materials with you. Yeah, and each of you will do a single project individually. So yeah, you won't be working in groups. And we will expect you to build, implement code, and design with close engagement with your supervisors. Yeah, so basically, depending on the project you will choose, you will be assigned a mentor that you will work closely, one or two mentors. And yeah, you can like always ask questions when you're stuck at something. And yeah, we will try to help as soon as possible and like keep you like working on your project. Yeah, and yeah, we basically also expect you to participate, ask questions, contribute thoughts and ideas, and read relevant papers. So like you don't necessarily have to stick to the like what we will define in the like project description. So if you like have new ideas, if you have read something that is like new and you think it will contribute to the idea, then yeah, you should discuss that with your supervisors, and we will see whether it makes sense to add it in the scope of the project or not. Okay, yeah, and if you do a really good work, yeah, it may even get published. So I think, yeah, that will be good for you. Okay, so there's the course website. You can access it using this link over here. It contains some useful information about the course, and I think I shared most of that information with you in the email that I sent. And yeah, so please check your email frequently for announcements. As I said, so if you like set up a something for instant messaging, we will use that instead because like mails are not always too convenient. Yeah. Okay, so here we have some required materials and recommended materials. These slides are already on the website. So after the meeting or during the meeting, check out these links and then please study these materials. Especially, I guess the tutorial video will be important, but maybe like to understand it better, you should also like cover the other materials first. Okay. Yeah, so we will hopefully in this meeting try to schedule a time for the second meeting. So it will be good to do it as soon as possible. So at the end, yeah, like in total, you have more time to work on your projects until the end of the semester. Yeah, and during this second meeting, we will announce projects that you will choose from, and yeah, you will work on a single project individually. Yeah. Okay, and like after these meetings, after these like general meetings, where we will discuss like the SoftMC tool and some works that were published from our group that use SoftMC, you will start working on your projects. And from that point on, you'll be having individual meetings with your mentors. So like, yeah, that will be more efficient for your process. For your progress that you'll make in this project. Okay, so we will have some tutorials and short talks, like about like characterizing DRAM, studies that characterize DRAM, and about SoftMC, the tool that we'll be using. And yeah, we'll cover some recent research works, mostly from our group. Yeah, and so this last bullet point, this is expected to happen at the end of the semester. Once you're done with your project, you will make a presentation and yeah, tell us, meaning the mentors in this course. And also like, I think we will announce this talk to the rest of the our Safari research group as well. So potentially we'll have more like bigger audience that you can describe your project to. Okay, cool. Yeah, so I think this was like everything I wanted to tell regarding like the course and like logistics. Any questions so far? Okay, so how many of you already studied the material or some of the material that I sent?
I did.
Yeah, I did.
Okay.
Me too.
Okay, you did what? Like, because like it's a lot of material, right? Did you like look at everything?
I watched the two videos and I read 3 studies.
Okay.
I read the paper describing SoftMC.
Mm-hmm.
Yeah, I watched the videos and read the first paper, and I'm not perfectly finished with the second one.
Okay. Yeah, I mean, I guess that's very good. So like you should like already have like some information about what I will be describing here. So basically I will go over this SoftMC talk. I think one of the videos was like that, the like SoftMC talk that I recorded at some point. Okay, cool. Yeah, so okay, then let's go over the slides. I will try to do this quickly. And yeah, when you have a question, just speak up. Don't wait for me to like ask for questions. Yeah, and like let's try to cover this quickly. Okay. Yeah, so this was the title of the paper, a flexible and practical open source infrastructure for enabling experimental DRAM studies. So you can see the authors here, and this was HPCA 2017, the conference at which this paper was published 4 years ago. So I will start with an executive summary. Two critical problems that DRAM has are reliability and performance. And there's a recently discovered hardware bug, we can call it, called RowHammer. And yeah, so I will explain. So basically, like the reason I mentioned RowHammer here is that it basically demonstrates a bit more like why like DRAM reliability is such an important problem. Yeah. And basically, in order to solve these two problems, it is important to characterize, analyze, and understand DRAM cell behavior. And to this end, we design and implement SoftMC, which is an FPGA-based DRAM testing infrastructure. We aimed for it to be flexible and easy to use, and we enable that with a C++ based API. And here's the source code on this GitHub repository. Although this is the older version, we still haven't publicly released the new version that supports DDR4. And you will be mainly working with that one. Yeah. And yeah, using SoftMC in this paper, we implemented 2 use cases: a retention time distribution test, where we look at how different cells in a DRAM chip. So basically, what is the retention time of different DRAM cells in the DRAM chip? And we try to see if like our findings correlate with prior studies that did the same. So the goal here is to validate the infrastructure that we have implemented. And the second use case is an experiment to validate 2 latency reduction mechanisms that were proposed based on like circuit level simulation, but they were never tested on real DRAM chips. Yeah, and like we hope that SoftMC enables a wide range of studies, and yeah, it facilitates future research in like DRAM. Okay, so here's the outline of the talks. I will start with some DRAM basics and motivation. A typical DRAM system, or like a typical system, consists of a CPU and a DRAM module, as you see over here. And there, the CPU implements a memory controller that communicates with the DRAM module over the memory bus. A single module consists of multiple DRAM chips, and inside every DRAM chip, we have a DRAM subarray or a DRAM bank. Let me see which terminology we use here. Well, I guess, okay, so let's say it is a subarray, right? And then in this subarray, the DRAM cells are organized as 2-dimensional array. And each DRAM cell stores a single bit information as electrical charge. The cells are vertically connected to sense amplifiers, and we call like these like vertical so we call this a column basically, the like vertical line of cells, and like the DRAM cells are horizontally organized as like DRAM rows. Okay, so let's look at DRAM commands that the memory controller issues to access a particular DRAM cell. And like this is the DRAM cell that we will try to access. Okay, so the first command, the first DRAM command that the memory controller sends is activate. So once like this command reaches the DRAM, what happens inside this subarray is this row that contains the cell that we want to access is getting activated. So during activation, the charge in these cells is shared with the sense amplifiers through the bit lines. So these like vertical lines are called bit lines. And the purpose of the sense amplifier here is to detect the small charge stored in each cell and amplify it to like both like to infer what value is stored with that little charge, either like 0 or 1, and then restore that charge back to the DRAM cell so we don't lose the data. So after this operation completes and like the cells, the row and the sense amplifiers are in this state, so they both contain the same data, let's say, the memory controller can issue a bunch of read or write commands depending on what it wants to do with this row, right? And here our goal was to read this cell, and with the read command, the sense amplifier that corresponds to that cell provides the data, and then that data is transferred over the memory bus to the memory controller. So this is how we get the data from the DRAM. But we are not done yet. In order to be able to access another row from this DRAM, we first need to close this row or precharge it. And for that purpose, the memory controller sends a precharge command. Yeah, and this precharge command does basically what I said. So it precharges the row and the sense amplifiers and reverts them to their initial state. So the DRAM now is ready to access another row by another activate command. So in this slide, I would like to show the status of a DRAM cell and a sense amplifier prior to performing the key DRAM operations and on the completion of them. So when the cell is not yet activated, in another row, when the row is closed, the DRAM cells leak their charge, right? And then here we define retention time like this: the interval during which the data is retained correctly in the DRAM cell without accessing it. So let's say the DRAM can store the data for at most 64 milliseconds. This means if it is not refreshed for more than 64 milliseconds, the data might be corrupted. And to prevent this, every DRAM cell is refreshed at fixed period, which is typically 64 milliseconds or sometimes 32 milliseconds. And yeah. Okay, so now let's go over this diagram that shows how the charge stored in the DRAM cell changes during like basically when we access the cell. So first, the memory controller issues this activate command, and once the DRAM cell starts sharing its charge with the sense amplifier, and the cell and the DRAM, the cell and the sense amplifier, sorry about the noise, reach this state, which happens after ready to access latency. So there is some time that we need to propagate this charge from the cell to the sense amplifier to get into this state. At this point, the memory controller can issue read commands to like read the data. And similarly, to be able to precharge the row, the memory controller needs to wait until the cell is fully restored, basically, as you see here in this diagram. And afterwards, we wait for the precharge latency, which basically resets the sense amplifier to its initial state. So it has to be discharged. And after that point, the memory controller can issue another activate command to activate another row, or maybe the same row. Okay, so what happens if we violate these timings? So why are we talking about violating these timings? It is because here, this is not strict timing in the sense that it is not embedded inside the DRAM chip, but instead the memory controller just obeys these timing parameters based on the DRAM datasheet, basically. but it doesn't have to. And then in the experiments that we will do, mostly in this course, in the project that we will work on, we will violate some of these timing parameters intentionally in order to like analyze their effects. Okay, so let's look at what happens when we, for example, read earlier than the ready to access latency. So here, when we try to do that read operation, we see that the sense amplifier contains like lower charge than it can be read reliably. And yeah, when this happens, basically, if we try to read when we read the sense amplifier at this state, we may not read the correct data that is stored in the DRAM cell. So similarly, if we precharge early, we may not restore the cell fully to its original charge amount. And as a result, when we activate the row again that contains this cell, it may lose its data. So like future accesses will get corrupted data. And similarly, if we activate earlier, before the sense amplifier is fully restored, this may destroy the data in the new cell that we try to read. Okay, is this all clear? I guess no questions then, yeah. So basically, violating latencies negatively affects the DRAM reliability. So you may get like different error mechanisms depending on which of these latencies you violate. So there are other factors affecting reliability and latency, and here's a list of that: temperature, voltage, intercell interference, a manufacturing process, retention time, and some other things. So I won't explain exactly how these affect the DRAM reliability and latency, but if you're interested, we can have a discussion about that. But these are mostly covered in the material that we sent you already. So yeah, you can take a look at that. So basically, to develop new mechanisms to improve DRAM reliability and latency, we need to better understand these effects, the effects of these factors. Okay, so many of the factors affecting DRAM reliability and latency cannot be properly modeled. So it could be either because of lack of information, or it is just like very difficult to do analytically. And yeah, because of that, we need to perform experimental studies using real DRAM chips. And this is what we will do in this course. Okay, and yeah, we will use this new tool that we developed called SoftMC. I think we named it like based on like software-based memory controller. So MC stands for memory controller. Okay, so we had several goals when designing this testing infrastructure, DRAM testing infrastructure. So we wanted to make it flexible, such that it enables testing any DRAM operation, and basically testing any DRAM operation, any combination of these DRAM operations with like custom timing parameters between them. So basically recall like those, like violating the timing parameters we discussed in the previous slide. So the infrastructure should be able to provide that. Second goal is to make it easy to use. And for that, we developed a simple programming interface, so you don't have to deal with like low-level hardware design. And most of the times you don't need to change the hardware at all. And yeah, so like this interface is providing minimal programming. Yeah, using this interface, you can develop your experiments with minimal programming effort and time. And we wanted to make it accessible to a wide range of users who may like experiencing hardware design. So like this is why we like yeah, designed this interface to begin with. So SoftMC in a high level. Okay, so let's look at this high level view of the SoftMC infrastructure. So you can see a picture of it here. So it is an FPGA-based memory characterization infrastructure that is typically composed of these components, right? So we have an FPGA that has the DRAM module mounted on. So like it's not very well visible, but yeah, so here's the module. And this FPGA is connected to the PCIe interface to a host machine, where we develop the programs, where we run the programs, and like collect data from DRAM to analyze it later. So in this picture, you can also see a heater inside a heat chamber and a temperature controller. So the reason we built this heating infrastructure is basically to control the ambient temperature of the DRAM, because many aspects of DRAM, such as retention time, is significantly affected by the temperature of the DRAM chips. So yeah, some studies require precise control of the DRAM temperature in order to have like reproducible results. Okay, so this first prototype was done using this FPGA, Xilinx ML605. Yeah, that's not such an important information. And yeah, it is easily programmable using a C++ API, as I said previously. Okay, so let's look at the key components of SoftMC in a bit more detail. We will start with the SoftMC API. So this is the previous version that is available in the GitHub repo, but I will also show you the new API of the new version that you will be working with. Okay, so in this code here, so this is a C code. We show basically a code piece that you can use to write data to a DRAM row. So, okay, what happens here? We have functions that we call instruction generator functions. So by calling these functions, basically you insert to the instruction sequence instructions that will be executed in the DRAM. So the first instruction over here is activate. So like as we covered in the previous slides, activate is opening a row from a DRAM bank. So in a single DRAM chip or in a single DRAM module, we can say we have multiple banks that operate independently. So you can access, let's say, row 1 from bank 0 and then row 1 from bank 1. So these two rows are different. They're like physically in different locations in DRAM. Okay, and then like we insert some wait. So this is a wait instruction that specifically waits for TRCD, which stands for the the activate to read latency, or activate to read write latency. Yeah, and so here, this is how you tune for how long you want to wait between two consecutive DRAM commands. And the third command here is write. So yeah, previously we covered read, and here we are performing write. So let's look at the parameters that we pass to this write command. So it is the bank, right? To which bank we want to write to. We do not specify the row because in a single bank, we can have only one row open. But in multiple banks, we can have, well, each bank can have at most one row that is open, right? So it is clear from which row we will read. But we specify the column to read from. So a single write command is not writing to the entire row, but it is only writing to a portion of it. And that portion, the size of that portion is typically 64 bytes, which is like equal to the cache line size in typical systems. And the last parameter over here is the data, right? So what data we will write to this particular column. Okay, and then we wait again. And this is the latency that we need to wait for this write operation to go through. And then we issue the precharge operation, then wait again, and then this is the end of the program. And this end instruction specifies that the program is finished. If you don't specify it, yeah, it results in an error, basically. And then this last line over here starts the execution of this instruction sequence. So basically, all these instructions that are highlighted here are basically inserting something to the instruction sequence, are inserting commands to the instruction sequence or instructions to the instruction sequence. Yeah, and once we call this function, the execute function, this instruction sequence is really sent to the FPGA and executed there. Okay. Oh, I had animations. Okay. Yeah. And this is the new API. So it looks slightly different. So here, I guess the approach is quite different in this new API. So we do not have instruction sequence anymore, but we have a program. And what is the difference? So here, you can think of this as a like first, so you can think of it as some sort of a queue, basically, right? So once one of these commands is executed, it is gone, basically, it is consumed, right? So, but in the program, we can reuse these instructions by forming loops, as in like typical, or conventional like C++ or Python programs that I assume you typically write. Okay, so we have some functions that I would like to highlight over here. Okay, so first we have 3 different classes, SoftMC platform, program, and SoftMC instructions. In SoftMC platform, we have 2 key functions, execute and receive data. The first one is used to start an execution of a program, and the second one is used to receive data from the FPGA through the PCA interface. And the program class contains a few instructions too. One of them is to add a new instruction into the program. The second function is to add a branch. So we support a few branch types, such as like branch if equal, branch if not equal, branch if less. So if you're familiar with any instruction set architecture, if you have ever programmed at that level, at like assembly level, you'll be familiar with those. And we have an instruction to add labels that specify the like basically branch targets, where to jump when that conditional branch is satisfied. Okay, so if this is unclear, this is important to, this is important that you ask a question here, because like in the past incarnations of this course, I had like issues with some students that like didn't know exactly what is a like instruction. And yeah, they had difficulty in understanding these concepts. Okay, I assume that is not the case this time. Okay, and yeah, so what are the instructions that are supported by this new SoftMC version? You can see some of them here. We listed them into 3 categories. The first is arithmetic and logic instructions, such as AND, OR, XOR, add, subtraction, and yeah, more instructions over here. We have some scratchpad memory instructions. So these load and store data not to the DRAM, but some other memory that is implemented inside the FPGA. Okay, so like you use these instructions in case you want to temporally store some variables in your program. And the last set of instructions here are the DRAM commands that we covered already, such as like activate, precharge, read, write, and refresh. So these are the, I think, 5 that you'll be using mostly. Okay, so let's cover the second component, which is the PCIe driver. So actually, I won't cover it in too much detail. It is just like driver that we implement using this RIFA tool that you see a reference to at the bottom of the slide. And yeah, if you're interested in how it works, so you can check this out. Okay, and I will jump to the third component, which is the hardware implementation of SoftMC. Okay, so here's a simplified diagram of like what is happening inside the FPGA. We also show the host machine and the DRAM, and I will explain how this operates by going over an example. So in the host machine, as the user, we basically prepare the instruction sequence, right? So like here, this is the old hardware, let's say, and we deal with these instructions or instruction sequences. Okay, once we have the instruction sequence ready, we call that execute function, and this instruction sequence is sent to the FPGA and temporally stored in the instruction queue. And after receiving all the instructions, the FPGA starts executing these. So the first instruction over here happens to be an activate, and the instruction dispatcher forwards this activate to the DRAM over the DDR PHY module that you see here. It's not important exactly what this PHY does, but it basically communicates with the DRAM at a low level. Okay, so like this, basically we are done with this first instruction, right? So it produced a DRAM activate command, and the DRAM, and that command was issued to the DRAM. Okay, let's see what is the second instruction. It is a wait instruction, and its parameter is equal to the ready to access latency. Okay, so it does nothing basically, just insert some like bubbles, some like idle cycles where we do nothing, but just like let some time pass. Okay, and the third instruction is a read. So this again, once executed, produces a DRAM command, a DRAM read command, and reads some portion of the row that we activated. So this time the DRAM returns data, well, because like obviously we want to read data, and that data is that data is captured in the read capture module over here, and later sent to the FPGA to the host machine over the PCIe controller. So this is basically how the hardware operates at a high level. We have some other modules that I won't go into too much detail, but these are doing some maintenance operations. So the calibration controller over here is like handling, is issuing periodically some operations that deal with signal integrity of the DRAM, like of the physical DRAM interface. And the auto refresh controller, if enabled by the user, periodically issues refresh commands to the DRAM. So you can enable this when you don't want to deal with refresh commands at the program, but you want the hardware to take care of that automatically. And you can configure the interval at which to issue these auto refresh commands. Okay, so in this slide, let's look at the new hardware design. It is mostly the same. At least here, it is depicted very similar to like the old version. So what changed here is instead of the instruction receiver in the previous slide, we have a simple processor. And yeah, we deal with some arithmetic instructions as I showed in the previous slide, right? And we have a program and a program counter. So this is looks in this sense very similar to like a simple CPU, like yeah, that you are familiar, I assume, from the computer architecture classes YouTube. Okay, and so here, instead of like having an instruction sequence at the host machine side, we have a SoftMC program. And this program is sent at once. I don't have animations here in this slide, but this program is sent at once and stored in the program in the simple processor. And then the simple processor starts executing this program in a way very similar to how processors execute programs, right? So we have a program counter that points to the next instruction to be executed. And as we execute these instructions, the program counter is incremented, or it is set to another like location in the program if it encounters branch or jump instructions. Okay, and the rest is pretty much the same. Okay, cool.
Can I just ask you real quick?
Yeah, sure.
Because FPGAs are much slower than DRAM, so can you access DRAM in every clock cycle, or?
Yeah, good question. Yeah, so you're right about that. So there's a maximum frequency that FPGA support for the DRAM interface. So this FPGA that we use, I think, can be clocked at most 800 data rate. No, 800. Wait, I just don't want to give you the wrong number. Yeah, so it should be 400 megahertz. And since this is DDR, which stands for double data rate, we get like 800 data rate. Yeah, I think that's correct. So basically, the DRAM interface can be clocked max at 400 megahertz, but the FPGA logic, the logic that you see here with these like colorful blocks, operate at half of that. They operate at 200 megahertz. Yeah, so basically here in the interface, we do something that is sometimes referred to as hot clocking. And what happens basically is we effectively issue 2 commands at each cycle. And the interface is executing these 2 commands one after another at 2 times the frequency at which this side operates on. Is it clear, or should I go into a bit more detail?
I mean, yeah.
Yeah, so basically here, okay, so I like depicted it as like this instruction dispatcher is preparing 1 instruction, but it is in practice preparing 2 instructions at each cycle. And it sends 2 instructions to the DRAM PHY, and the DRAM phi operates at 2 times the frequency of this part. Basically, this part is operating at 1x, and the DDR phi at each let's say FPGA cycle is sending 2 commands to the DRAM. Well, not every time, right? So if you have a wait instruction, so if you don't need to send 2 instructions in back-to-back cycles, then we have only one of these 2 instructions here. Yeah, so at most 2. Okay.
And just another question. You said that when we execute a read, right, that it outputs the bit to the computer. So can we even interact with the value that we read, or can we just analyze it later?
Yeah, so not on the FPGA, but you can read that data as is back to the host machine and do whatever you want with it, right? So you can store it on the disk, or you can check if it contains bit flips, like errors, and like do some analysis based on that. Just to clarify one more thing, because like you said, we read a bit. So like I tried to explain it more simply in the previous slide, like as we are accessing a single cell, but in like using the interface, the DDR3 or DDR4 interface implemented today, we are reading data at larger granularity. Typically, we are reading 64 bytes at once with each read command, or we are writing 64 bytes with each write command. Okay, yeah, and if you want to look at specific bit within these 64 bytes, you have to do that in the host machine in your C++ program. Okay, cool. Yeah, it is good that you asked that question. I guess like I never mentioned it. Okay, so let's jump into the 2 use cases that we implemented using SoftMC. So the first use case is a retention time study. And retention time of a DRAM cell is defined as the interval during which DRAM can correctly store its data, as I told you in the previous slide. So in this test, we experimentally analyzed the retention time distribution of 3 DRAM modules from 3 different vendors. And now I will show you like the steps that we basically perform using SoftMC in order to do that retention time distribution study. So we first start with writing reference data. It could be all ones or all zeros. And we initialize an entire row using this reference data. Okay, so maybe one more thing that I will clarify here. So like usually a DRAM cell leaks from charge state to discharge state, right? So it loses charge. But that does not mean charge state always indicates a bit that is like set to value 1, right? So it could be 0 as well. And that is as a result of some inversion happening in the DRAM circuitry. So this is why we sometimes experiment with all zeros instead of all ones. Sometimes the charge state in some rows or in all rows, depends on the DRAM design, can be when we store zeros in that DRAM. Okay, and so here you can see the C code that we can use to initialize an entire row with some known data. Okay, I won't go over this, but it is like quite like short code. It is only 12 lines. And after what we do, we wait for some refresh interval. So this is the refresh interval that we want to test, basically, right? So let's say we want to test if the cells in this DRAM row can retain their data for 10 seconds. Then here we wait for 10 seconds. And afterwards, we read the data back and check for bit flips. If this row contains bit flips, yeah, then we probably achieved our goal, because like we know like for how long the weakest cell in that DRAM can store the data correctly. But if we do not observe errors, we can increase the refresh interval, and instead of let's say 10 seconds, we can wait for 11 seconds. and go back to this first step and try again. Okay, and so you can do this, like you can do a similar experiment also to analyze each cell individually, not at a row granularity, but you can profile the retention time of each cell in that row individually instead of just the weakest cell in the row. And this entire thing can be implemented with just 100 lines of C++ code. And so here I will go over the results. So basically our results match the retention time results reported by prior work. And this study validates the correctness of our testing infrastructure. But so let me go a little bit about like what this plot is exactly showing. So on the x-axis, we have the refresh interval in seconds. And on the y-axis, we have the number of erroneous bytes, right? So this means like, if we have at least one bit flip in a byte, we count that, right? And that it contributes to this y-axis. And like different modules are indicated by different colors. So we have module A, B, C. And this test was conducted at room temperature. Not at like high temperatures where usually DRAM cells leak their charge faster. Okay, so one thing I want to emphasize here is that as you see at room temperature, DRAM cells are pretty strong. So if you remember, I said a DRAM typically refreshes all of its cells at 64 milliseconds. But here we can see that we get no bit flips. Well, maybe to the point somewhere close to 2 seconds. So that's a lot. Yeah, but still all the DRAM cells are refreshed at fixed interval, 64 milliseconds, because manufacturers cannot guarantee that you won't have a weak cell, really weak cell that will retain its data for slightly more than 64 milliseconds. So they don't want to have any such like retention failures, right? So all cells should ideally operate correctly. Okay, so and yeah, so like I don't have a another plot showing that, but prior work also reported similar observations regarding like this trend, like how the number of bit flips change with the retention interval. And so here we conclude that, yeah, our infrastructure works correctly, and then we can observe similar results. Okay, the second use case is a bit more complicated. So here we evaluate two, well, it says recently proposed here, but they are not recently like anymore. This was a study done like 4 years ago, right? And we basically show the effectiveness of SoftMC in validating or refuting recently proposed ideas, or like any ideas in general. Okay, so the two mechanisms that we will look at are charge cache and NUAT, which stands for non-uniform access time memory controller. So they exploit the same key observation to reduce the DRAM access latency. And this is observation, right? A highly charged cell can be accessed with low latency. So let me try to explain that here. So yeah, so here, this is ideally what a DRAM cell charge will look like right after it is refreshed, right? So it is fully charged. But this is not always the case. So like depending on at which point during the 64 milliseconds refresh period you access this DRAM cell, it contains different amount of charge. So like this charge is still sufficient to read the data correctly, but not if you violate, let's say, this read to access latency in purpose. So basically what I'm trying to say is, if the DRAM cell is fully charged, you have a chance that you will read the data correctly, even if you reduce the ready to access latency by some amount. Okay, and let me try to illustrate it here. Well, I don't have an animation for that. Yeah, sorry for that. But yeah, basically here the point is that we can reduce both ready to access latency and activation latency by taking advantage of this observation, right? So like if you have less charge in the cell, we will need more time in order to propagate this charge into the sense amplifier. And basically the entire process will be much slower compared to having a fully charged cell. And this ready to access latency and activation latency is basically set based on this worst case condition, which is like if I animate it back, the state of the DRAM cell that is just about to be refreshed, right? But if that's not the case, if the DRAM cell is fully charged, you can potentially potentially have some slack basically in these timing parameters that can be exploited. Okay, so we basically test this hypothesis, right? So this like observation that, or this idea that these fireworks propose. And here's how we test that. We again first start with writing some reference data to the DRAM, and then we wait for wait interval. So here, this is not the time we wait for to get a retention failure, but this is the time we wait for to let the cells leak some of their charge, but not all their charge, right? So, I mean, hopefully after this wait interval, the cells can still be accessed correctly if we access them with the default access latencies. And here, longer we wait, we expect to have lower cell charge, and shorter we wait, we expect to have higher cell charge. And afterwards, we read the data back. So here, we sweep the ready to access latency parameters, right? So the ready to access latency parameter, sorry. And yeah, so as I said, so if you have wait for longer, we ideally expect that we are able to read the data correctly, even if you reduce this ready to access latency parameter a little bit. And yeah, so like as in the previous experiment, we in the next step try to observe if you have any bit flips, and then we can repeat this by changing the wait interval in this experiment. And at the same time, we can also sweep the ready to access parameter that we test with. Okay, so in this experiment, we basically have these two parameters that we can play with. Okay, and yeah. And this we implemented, I think, with about 150 lines of code. Okay, and like these numbers are just to like point out that you can use SoftMC to like implement things quickly, right? So they don't take too much effort. Well, if that can be measured correctly with the number of lines, you're right. Usually not, but I guess this is the metric we could have gathered at that time. Okay, so based on these studies, based on the like key ideas of the key idea of these studies, we expect to see something like in this plot, right? And here we have the number of erroneous bytes again on the y-axis, and the refresh interval on the x-axis. And different colors represent different ready-to-access latencies. Yeah, okay, so what happens here? So if we access with ready-to-access latency 6, which is the default ready-to-access latency, you can see that we can keep correctly accessing the DRAM cell for like pretty high refresh intervals, right? But that is, yeah, to like somewhere at this point, basically. But that's not the case if we try to access the cell with lower ready-to-access latency. So you can see that with 3 or 4, and even with 5 cycles of latency, we get some bit flips. Yeah, and so I guess here is the point where we can correctly access with any of these latencies, right? With 3, 4, 5, and 6. So basically, yeah, so this is the margin that we can exploit with these mechanisms. Okay, but do we see this in the real data that we obtained from real DRAM chips? And yeah, the answer is no, basically. We do not see this expected effect. So what we see instead is, yeah, all the latencies like 6, 5, and 4 follow a very similar trend. They like overlap pretty nicely. We don't see this distinction in the expected curves. The only latency that basically deviates from the others is when we have 3 cycles of latency. And like this is not useful either, because like as you see here, like even when the wait interval is very small, it is 8 milliseconds, which is much lower than the default refresh interval of 64 milliseconds. We still cannot read the DRAM correctly. We get a lot of errors. So yeah, basically we cannot use this latency at any wait interval. Yeah, so basically what these works propose is not working, at least with the current DRAM chips that we have. Yeah, and send them animations that I only use my mouse to point. Okay, so basically, yeah, we do not observe the expected latency reduction effect in existing DRAM chips. But why is that? The key idea of this works makes sense, it is sound, but why do we not observe this? So we don't know exactly why, but we have a hypothesis. So the memory controller cannot externally control when a sense amplifier gets enabled in existing DRAM chips. So I said that the memory controller has control on some of the timing parameters, right? So it can decide when to issue a read command, for example, after an activate command. But there are some timings that are controlled inside the DRAM chip. And we suspect that one of these timings is the reason why we do not observe the expected effect. Okay, so let me try to explain that. So here we have the cell charge initially somewhere in this data 1 region. And we have the sense amplifier here in the middle, which just shows that the sense amplifier is pre-charged, right? So it is like ready to sense some data. And here we draw a line representing the ready to access charge level. So this is basically like when the sense amplifier reaches this point, when we read this cell, it is when it is safe to issue a read command. Okay, once we start with the activation, what happens is the cell shares its charge with the sense amplifier, and they both like converge to some point over here. And this is basically what this sentence over here means, right? So like this is the point where the sense amplifier is getting enabled to start restoring the charge that it has sensed. So we cannot play with this time. So this is controlled by some like fixed timing inside the DRAM circuit, right? So like after, let's say, n nanoseconds after receiving the activate command, the sense amplifier starts restoring the data, restoring the charge back to the cell. Yeah, and then this is a fixed latency. And yeah, so once the sense amplifier starts restoring, they like both the sense amplifier charge and the DRAM cell charge basically start increasing. And at this point, where the sense amplifier reaches this point, we can issue the read or write command. Okay, but basically, we suspect that if you were able to do this differently, right? If you were able to activate the sense amplifier a bit sooner, we can potentially reduce some latency and access the DRAM faster. Okay, and then why we suspect that it should be possible reducing this latency is simply because the sense amplifier reaches the same voltage level or the same charge level that it reached previously with this blue line over here. It reaches it much sooner because like the initial charge that we can share with the sense amplifier is much higher. Okay, that's the idea. Yeah, hopefully it's clear. Okay, yeah, so this was like about the second use case, and hopefully like I managed to explain why we are not seeing the expected effect. So it's not necessarily that the mechanism proposed in this mechanism is wrong, but we just cannot observe it in real DRAM chips implemented today or available today, I should say. Okay. And yeah, so I presented these use cases. Let me talk about some future research directions that we believe SoftMC can enable. And in fact, it's enabled some of those already since we first presented this work. Okay, so yeah, so we expect SoftMC to enable more characterization studies of DRAM. Specifically, how are the cell characteristics changing with different generations of technology nodes? And so like as like manufacturers improve their designs, they usually scale their technology nodes, and basically doing so they can fit more cells into the same area, right? So like they increase the DRAM cell density. And yeah, so like exploring how such scaling would affect different DRAM characteristics is something that can be explored with SoftMC. What types of usage of the DRAM cell accelerate aging? Not sure if you are familiar with this concept, but integrated circuits have aging effects. Like when you like use them, when you like stress them more and more, they start operating not as good as like before. Yeah, and like this is called the basically aging. Yeah, so like exploring these aging effects in DRAM can be done using SoftMC. It could also be, so SoftMC can also be adapted to support non-volatile memories. So these are mostly like the emerging memories that that people are working on, right? So like there are already modules available that support interfaces very similar to DDR interfaces originally used for like accessing DRAM. And yeah, potentially SoftMC can be adapted to support these interfaces and also study non-volatile memories. And yeah, so some other extensions can also be made to study other things such as memory scheduling and power management. And also analyze workload and how like workloads interact with DRAM and how they like changes in DRAM. Let's say when you change the ready to access latency, how that affects workloads, right? So how much, how faster these workloads become. So like you can potentially look at these things. And SoftMC can also be used as a testbed for in-memory computation. Yeah, I'm not actually sure if you already have a project on this, but yeah, I think we do something. We do have something in this direction. Okay, anyway, so yeah, as a conclusion, we designed and implemented SoftMC, the first publicly available FPGA-based DRAM testing infrastructure. We tried to make it flexible and easy to use. And in this study, we implemented 2 use cases to show like the first a retention time distribution study to validate that our infrastructure is working correctly. And second, we show that the expected latency reduction effect of 2 recently proposed mechanisms is not observable in real DRAM chips that we have today. Yeah, and we believe SoftMC can enable many other studies that we just discussed, ideas and methodologies, and help design future memory systems. And this is the link. You can check it out if you want for the old version of SoftMC, as I mentioned several times. Okay, yeah. So finally, this is the end of the presentation, and yeah. So let me know if you have any questions about this, like technical questions or any questions about the course in general.
Yeah, I was just wondering if we like look at it from the perspective of RowHammer. Does a malicious program like running in the CPU have access to these parameters, like refresh time and this?
I guess you mean in like conventional, like commercial systems, right?
Yeah, exactly. If you would like infect a normal computer, like.
Yeah, so I guess the answer is no. And so like, okay, so let me go into a bit more detail. So an unprivileged attacker should not be able to change any of these parameters. But CPUs and the like BIOS specifically provide some configuration knobs that you can play with to tune some of the DRAM parameters. So I'm pretty sure that some motherboards enable you to change how often DRAM will be refreshed and also play with some of the latencies. So the ready to access latency that I described, so that you can play with. You can play with the activation latency, you can play with pre-charge latency and some other parameters. But like an unprivileged attacker should not be able to change those. Like even using like RowHammer, because like these are not stored in the, well, actually, yeah. Okay, yeah. So with RowHammer, I believe it should not be possible because like these configurations are not stored in main memory, right? Those are probably implemented as memory mapped registers in the CPU. So you have to go change something in the CPU to change how often DRAM is getting refreshed.
Yeah, okay, thank you.
And the memory controller is on the motherboard, right?
Oh, that was the case before, but not anymore.
Yeah, so because of DDR5, right? So doesn't it change everything?
No, even before DDR5. with DDR4 and also some DDR3s. So okay, so there was something called frontside bus, FSB, frontside buffer. Yeah, I think it was called frontside buffer, or Intel called it that way. So it was a separate chip on the motherboard that the CPU was communicating to access the DRAM. So it was like sort of a relay in between. But like later, as many other components, they incorporated that in the CPU. Right, so like the memory controller since then is part of the CPU, and we don't have frontside buffer anymore. I think it's it's frontside bus, not buffer. Yeah, so let me make sure so I don't use the wrong terminology. Yeah, it's frontside bus, FSB. Okay, anyway, yeah, but like even with DDR3, so like it entirely depends on the CPU, right? So here, not the DRAM. So the DRAM is the same, but if you have a very old CPU that needs a frontside bus, then yeah, the memory controller is not part of the CPU. But all new, and by new I mean newer CPUs manufactured before 2010. I cannot give an exact year right now, but yeah. But of course, like it is design dependent, right? So like I said that, but there might be systems that still use something similar. They still like implement the memory controller as part of the chipset, not as part of the CPU. Okay. Yeah, I guess we are done then, right? If you don't have any other questions. Yeah, I hope this was like useful. I like tried to explain like how SoftMC operates, and like this will be tool that you're mostly using. But yeah, so like I will suggest you to watch that tutorial video maybe like one more time later when you feel like it will be good like to go over the details again and like understand it a bit more, because like just watching it one time may not be sufficient to understand everything, but maybe like you will refer to that tutorial video once you start programming. All right, so once you start working on your project, I mean. Okay, should we try to schedule a time for the next meeting? So I would like to do it early next week, if we can schedule that. Yeah, so by the way, I apologize for having this meeting late, but it is difficult to schedule because like this is not part of your like typical lectures, and yeah, it will be just very likely that you have some other lectures at the times that I'm going to propose at reasonable hours. So this is why for this first meeting we did like 7, but it doesn't have to be that way. And well, so okay, so how about Tuesday morning? Is like 10 a.m. a good time for everybody?
Yeah, sure.
I would be at the university, so I don't know, because I have a lecture from 8 to 10, but I guess, yeah.
8 to 10. Okay. So is 11 better then?
Sure.
Okay. I guess then 11 is good for everybody. Okay, let me tentatively schedule this. Okay, cool. Yeah, and I will announce this later. I will send an email to make this official.
Or,
okay,
you
cool.
know, like I'm fine with 10:30. It's just, I just have to find some place, you know, to set up my laptop and stuff. So it doesn't have to be at 11, you know.
Okay. Okay, then, yeah, I think earlier the better. So let's say 10:30 for now, and let's plan for, okay, so this one may take long because we want to cover some example studies, right? So some like works that we did and published using SoftMC. And we will have some like multiple speakers based on that day. I think I will present 1 or 2 works, and then we'll have like several of the like other mentors presenting their works. And I think the plan is to cover 4 of these works. So assuming each of them takes like about 20 to 30 minutes. So this may take like something close to 2 hours. Well, it will be recorded. You don't have to like stay for the entire duration, but okay, so let's plan for 2 hours and we will start at 10:30. Okay, cool. Yeah, I will send an email and make this official later.
Okay. Earlier I asked because of the Moodle. It turns out that I do have access to the Moodle actually, but the link on the website is just from the spring semester. That's why I couldn't access it.
Interesting. Okay. Let me check that and fix if that is really the case. No, I think the link is correct.
Yeah,
Okay.
I think the point is that we already are enrolled, and the link is for enrollment of the course. So if I visit my Moodle page, I have perfect access to the whole course.
Wait, you're right. Something is weird. It is not last year's or last semesters, but I think we have duplicates. Oh no, it says spring semester, but it is so confusing. Okay, yeah, I think you're right. This is spring semester. Okay, yeah, I'll fix the link.
Okay,
I'll fix the link. Yeah.
Also, we are 5th semester ITED students, and we didn't really have a computer architecture course, but we do know how to program C++, and we had a computer, what's it called? Computer
engineering. That's that's what he means. You know?
Yes.
Okay.
Which was more like a MIPS architecture with CPUs.
Yeah, I think that's good, and yeah, should be sufficient if you have like good understanding of these concepts. Yeah.
Okay, sure.
Okay, cool. Then yeah, I will talk to you later.
I just have another question because I'm enrolled in another PNS at Safari, and I didn't get the email.
Which one?
The Remulator one, you know, designing the memory systems with Remulator.
Ooh, interesting. Are you sure you're like enrolled in that?
Yep. I also have access to Moodle with from that PNS, but I didn't get an email.
Okay. Well, the problem is, so I am usually informed. So okay, so like for some reason I can't see like who's enrolled in the like main ETH system, where like we have the regular courses. These PNS courses are weird. And yeah, so like I didn't get an email about like having any students register for this Remulator course. So this is why I like never initiated anything. But yeah, since you are taking it, okay, thanks for letting me know. I'll yeah, do something about it and like start that course too.
Okay, thanks.
But like you are like decided on that, right? So like you are gonna take it for sure.
Yep.
Because I think you'll be the only student, or at least I have to confirm.
No, I think there are 2 people there.
There are 2 people.
No, 3. 3, I think.
Okay. Well, you see that on Moodle?
No, I don't see it on Moodle, but when we were, you know, able to change our enrollments to PNS, you know, we had like access to the Excel spreadsheets, and you know, I saw that there were 3 people there.
Also, we received an email with the courses we are enrolled in. So.
Yep. Yeah.
Okay. Wait, are any of you also like enrolled in this Remulator course, or is it only one of you?
No, I'm just in this one and the homogeneous systems one.
Okay.
Yeah, but I got an email that confirmed that I'm enrolled in the Remulator one. So.
Okay. Yep. Okay. Yeah. So okay, I will get in touch with you and like other students too. Soon, probably like either over the weekend or next week. Okay.
Okay. Yeah.
Cool. Yeah. Okay. And yeah, thanks for coming to the lecture. And yeah, I will talk to you during the next meeting next week.
See you then.
Okay.
Thank
See you.
you.
Bye bye.
Bye bye.
Good evening.